Our first speaker of the morning is Priyanka Ganesan, and she's going to speak to us about spectral bounds for chromatic number of quantum graphs. Take it away.
Yeah, thank you. Hello, everyone. Thank you so much to the organizers for putting this together at such a short notice. And I especially appreciate this because I'm currently in the job market and I'm much needed to go to the JMM. So thank you so much. And thank you all for coming to my talk today. My name is Priyanka Ganesan, and I'm a fifth-year PhD student at Texas A&M. And today I'm going to talk about quantum graphs and spectral bounds for their chromatic numbers. So here is an outline of my talk. I'm going to begin with defining the quantum analog of a graph, and then talk about different approaches to quantum graphs, and then introduce a chromatic number for the quantum graph, and then conclude with some bounds, some lower bounds for these chromatic numbers. So let's get started. I first want to recall how it's like. So a classical graph has vertices and edges, and this structure can be expressed using an adjacency matrix. So here is an example of a simple graph on 3 vertices. I denote the vertex set by 1, 2, 3, and the edges by these tuples, 1, 2, 1, 3. I'm going to assume that my graph is undirected. So 1, 2, and 2, 1 means the same thing here. And this structure of the graph can be expressed using a single matrix known as the adjacency matrix. The entries of the adjacency matrix has zeros and ones, and the positions of the ones represent an edge, and the positions of the zeros represent a non-edge. So for example, here in this example, the first row, third column has a 1, which means that 1 and 3 are connected by an edge. Whereas the second row, third column has a 0, which means that 2 and 3 are not connected by an edge. So in this way, the entire structure of the graph can be encoded using a single matrix. And what we can do is replace this 1 by any non-zero number, and we could still extract the same information from that matrix. So even if we replaced these ones by all different non-zero numbers and get a matrix of this form where the stars are all different non-zero numbers, we would still get the same information about the graph. So one way to generalize a classical graph is by generalizing this structure, the skeleton of this adjacency matrix. So look at the set of all matrices that have elements or entries similar to the adjacency matrix, but you allow the positions of the ones to be replaced by any complex valued numbers, and these could be all different. So I'm going to omit the condition that the star has to be necessarily non-zero, because by doing this, the set SG defined here will then become a subspace, which is a nice property to have. So we are going to look at matrices of this form that are similar to the adjacency matrix, but the ones are replaced by different complex value numbers. And in this particular case, it's just a subspace. But if you further assume that the graph is reflexive, which means that there is a loop around each of these edges, then we also get the additional property that the identity matrix belongs to this set. So now to summarize the properties of this set, it is first of all a linear subspace. Then secondly, it's going to be closed under adjoint because I'm assuming that my graph is undirected. And then since the graph is reflexive, it's going to contain the identity. So in summary, it's going to be an operator system in this matrix algebra. Just to recall what an operator system is, it's a subspace in the set of bounded operators over a Hilbert space, such that it contains the identity operator and is closed under adjoint. So that is exactly what this set SG was satisfying. So basically, we could generalize the adjacency matrix of a graph into an operator system that still gives us the same information. So this is the key idea of a quantum graph. So here is a definition of a non-commutative graph associated with a classical graph. And this is exactly what I was defining earlier. So if you begin with a classical graph G on some n vertices, then you can associate an operator system with this classical graph using the idea that I said earlier, that you look at the span of the matrix units Eij, where Ij represents a position of the edge in the classical graph, or it represents a loop on the vertices. And this set is going to be an operator system in the matrix algebra, and we're going to call it the non-commutative graph associated with this classical graph. Now, we can clearly see that this set is going to be an operator system, but not every operator system in a matrix algebra can be traced back to a classical graph. So more generally, an operator system in a matrix algebra is called a matrix quantum graph, but it is not necessary that this comes from a classical graph G. If you want it to come from a classical graph G, it needs to satisfy another condition known as like bimodule condition over the diagonal algebra. So in summary, matrix quantum graphs are just operator systems in MN. Okay, so why would one be interested in studying such objects? So one motivation for studying matrix quantum graphs comes from information theory. So in information theory, the goal is to transmit information through a channel with minimum error or confusion. And so in case of a classical channel, we have this confusion or noise in the channel represented by a graph known as the confusibility graph. So here is an example. Let's say there are some alphabets x1, x2, x5 that are transmitted through a channel and are received as y1, y2, y5. Now, when information is transmitted through the channel, there is a possibility of noise addition. So B and V might be received as the same element on the other end. So this confusion is represented by these arrows that you see here. So both x1 and x2 might be received as y1. And so this confusion in the channel is expressed using this confusibility graph. The input messages of this confusibility graph are essentially, the vertices of the confusibility graph are essentially these input messages. And two of the vertices are connected by an edge if they can be confused upon transmission. So what I mean by that is that two of these messages can be received as the same output. So if you look at the graph, x1 and x5 never lead to the same output. And so x1 and x5 are not connected by an edge. Whereas if x1 and x2 can be received as the same output, then they are connected by an edge. So basically this graph associated with the channel is known as the confusibility graph of the classical channel. And in particular, when we replace this channel by a quantum channel, then the structure that you get here is a quantum graph. So basically, confusibility graphs of quantum channels are essentially quantum graphs. So mathematically, a quantum channel is just a completely positive and trace-preserving linear map. And the way quantum graphs were first introduced in information theory is as non-commutative confusibility graphs. So you begin with a quantum channel phi that is taking some m messages and outputting n messages. Let's say this quantum channel can be expressed as this. So this is a Krauss representation for any completely positive map that is also trace preserving. So then you can associate an operator system with this channel that is defined as given here. So it's the span of the product of the Krauss operators that occurs in this representation. And one can check that this will be an operator system. And in fact, it is exactly the non-commutative graph in the case of a quantum channel, the confusibility graph of a quantum channel. So one might think that this confusibility graph depends on the representation of the channel, but it can be shown that even if you choose a different Krauss representation for the quantum channel, you would still get an isomorphic operator system. So basically, this definition is independent of the representation that you choose for the quantum channel. And so how is it useful to study these quantum graphs? It's because two messages are not confusable upon transmission if and only if they satisfy some kind of orthogonality relation with respect to this quantum graph. And so if you know more about the quantum graph, then we can better know the capacity of the channel and how many messages can be transmitted through it without confusion. So that is a quick summary of the use of quantum graphs in information theory. But other than that, quantum graphs have also appeared in other branches of mathematics independently and have been studied in various disguises. So here is a short list of the main perspectives to quantum graphs. So the first one is quantum graphs can be viewed as a quantization of the confusibility graph. This is what I was saying on the previous slide. You can think of them as operator systems and matrix quantum graphs. But another way, which is more commonly used and is a generalization of this operator system picture, is viewing quantum graphs as quantum relations. This idea was proposed by Nick Weaver when he was studying quantum relations on a quantum set. And in this perspective, a quantum graph is viewed as a quantization of the edge set. And there is yet another way of defining quantum graphs, which is using a quantization of the adjacency matrix. And this approach was introduced by Musto, Royton, and Verdon while studying a categorical theory of quantum sets and quantum functions. So although these came up in different branches of mathematics like information theory, operator systems theory, and non-commutative topology, there is a nice connection between these different perspectives, which is using projections. So in each of these cases, you can define a projection map. In the first case, you can define a projection onto the operator system. In the second case, you can define a projection that places the non-commutative analog of the characteristic function on the edge set. And in the third case, you can define a projection using the quantum adjacency matrix. And then it can be shown that under appropriate identifications, all these projections lead to the same operator system. So in this way, all the different definitions of quantum graphs can be connected and traced back to the operator system idea. Okay, so I've talked about the first perspective already, so I want to briefly discuss about the other two perspectives before I jump onto the quantum graph coloring topic. So one way of looking at quantum graphs is as quantum relations. So in this case, a quantum set refers to a one-dimensional algebra, and a quantum relation on this quantum set is defined to be a weak star closed subspace in this P of H, that is a bimodule over the commutant of the quantum set M. So the motivation for this definition comes from the classical case. If you begin with just a finite set X and look at the quantum relations on L infinity of X, then you can see that there's a one-to-one correspondence between those quantum relations and the subsets of X cross X, so namely classical relations on X. So that's how this definition was motivated. And how can we use this to study graphs? That's because you can look at the edges of a graph as a relation on the vertex set. So you can think of the edges as a subset of V cross V, the vertex set. And in particular, if the graph is reflexive and undirected, then this relation is a reflexive and symmetric relation on V. And so a quantum graph can be defined as a reflexive and symmetric quantum relation on a quantum vertex set. So in this language, what this means is that the subspace S is a weak star closed subspace in over B of H. In B of H, that is a bimodule over the commutant of M. But in addition, it's reflexive, which means that the identity operator belongs to S. And it is symmetric, which means that it's closed under adjoint. So together, it's an operator system in B of H that is a bimodule over M prime. So that is how a quantum graph can be defined as a quantum relation. Another way of defining quantum graphs is viewing them as a projection with a quantum set. So this projection is motivated by the non-commutative analog of the characteristic function on the edge set. So in this perspective, you think of a quantum graph as a quantum set that comes with a projection living in M tensor M op, where M is a quantum vertex set and M op is the opposite algebra. And this P is basically a self-adjoint idempotent that satisfies reflexivity and symmetric condition. So the reflexivity means that if you multiply the two components in the tensor product, you get the unit element in M. And the symmetry means that if you swap the two tensor components, then you get back the same projection. And then you can again translate this definition back to the operator system perspective using a suitable identification. So, so far we have seen how to view quantum graphs as operator systems or projections. Another useful way of looking at quantum graphs is using the adjacency matrix. So this idea of a quantum graph was proposed by Musto-Reuter and Verdon. And in this case, you think of a quantum set as a finite dimensional C-star algebra that also has the structure of a Hilbert space. And in order to induce this Hilbert space structure, it's enough to fix a faithful tracial state on this algebra and then look at the GNS Hilbert space associated to it. Okay, so the way a quantum graph is defined in this perspective is that it's a quantum set, and then there is a quantum adjacency matrix which satisfies some nice conditions. And this adjacency matrix is nothing but a linear operator on this quantum set, which has this sure idempotent property, which means that its entries are precisely 0 and 1. And then it has a reflexivity property, say the diagonal elements are 1, and then it's also symmetric. So this is another way of looking at quantum graphs. And again, it can be connected to operator systems by defining a projection map. Okay, so in summary, a quantum graph can be expressed in different ways. It can be viewed as an operator system, as a quantum relation, or in terms of a projection, or using a quantum adjacency matrix. And in each case, you have some bimodule property or an idempotency condition, reflexivity, and undirectedness of the graph expressed in different ways. So that is an overview of quantum graphs and the different perspectives to quantum graphs. Now, what I'm interested in doing is study coloring of a quantum graph and its chromatic numbers. So here is the quantum graph coloring problem. For a classical graph, you know what a classical chromatic number is. So for example, if you think of the US map as a graph where every state represents a different vertex and the borders represent edges, then a coloring means that every state is given a unique color such that two states that share a border do not receive the same color. And the least number of colors you need is known as the classical chromatic number of the classical graph. Another way of defining a chromatic number for a classical graph is the quantum chromatic number, which is defined using a non-local game. So here you have two players, Alice and Bob, who are playing cooperatively against a referee. The referee sends them random vertices from the graph, and then they need to respond with color assignments to the graph. But the tricky part here is that they cannot communicate with one another once the game begins, so they don't know what the other person received as a question or responded as an answer. But together, their responses must satisfy a synchronicity condition and must respect the adjacency of the graph. And so the least number of colors they use in order to win this game is known as the quantum chromatic number of the classical graph. You can also define a classical chromatic number for a quantum graph using a partition of the basis of the operator system. But what is not clearly known is the quantum chromatic number of a quantum graph in terms of a non-local game. So this is what I did in my joint work with Mike Brannan and Sam Harris. So here we introduced a quantum to classical graph coloring game. The setup is an irreflexive quantum graph, and you pick a suitable basis for the operator system and the vertex set, and then define the inputs of the game to be elements from the suitably chosen basis for the operator system. And the referee sends the left leg of this tensor product to Alice and the right leg of the tensor product to Bob. And then they respond with classical color assignments. And in order for them to win the game, they must their responses must satisfy two conditions. One is the synchronicity property, which means that if they receive the same inputs, then they must respond with the same outputs. And then an adjacency property, which means that if they respond adjacent vertices from the graph, then they should respond with different colors. And the players can use several different strategies to correlate their answers, and this can lead to different notions of chromatic numbers. The simplest one is the classical strategy, which is just the usual chromatic number that we know. And then if they use some kind of quantum entanglement to correlate their answers, it leads to different kinds of quantum chromatic numbers for the quantum graph. So I will now talk about a combinatorial definition of the quantum chromatic number. So if you use the winning strategies of the game, it leads to some projection valued measures. And using those projection valued measures, you can cast this coloring in terms of a combinatorial way. And then that will give rise to the quantum chromatic number in a way that is useful for estimating the quantum chromatic number. So basically, there is a one-Neumann algebra N, which is a resource space that the players use to make joint measurements. And then there are projections living in M tensor N that have an annihilation property, that they annihilate any element coming from the operator system. And the least number of colors, or the least number of projections that go into this PVM, gives rise to the chromatic number. In particular, if N is just the complex valued numbers, then we get the classical chromatic number. If N is any finite dimensional algebra, then we get the quantum chromatic number. And if N is possibly infinite dimensional, then it gives the QC chromatic number. Okay, so I see that there is lesser time than I was thinking. So I'm going to end my talk with this definition of the quantum graph coloring, the combinatorial definition of quantum graph coloring. Okay, so thank you for your attention.